Good morning. Today we'll be talking about the basketball legend Steph Curry. Wait, that's not right. Sorry. We'll actually be talking about the lesser known basketball legend and computer scientist Steph Cook. So Steph Cook graduated from with a degree in mathematics from the University of Michigan in 1962, and then got his PhD shortly thereafter, also in math from a small little school called Harvard, something like that, in 1966. After graduating, he decided to work as an associate professor at Berkeley for 4 years, and then was denied reappointment by Berkeley, which I bet they regret now. So he then joined the faculty at the University of Toronto in the computer science and math department in 1970 as an associate professor. He was later, 5 years later, in fact, promoted to a regular professor, and then 10 years later, he was promoted once more to a distinguished professor, aka he got tenure, and was also just really good at what he did. So what is it that he did? Well, in 1971, while he worked as an associate professor, Cook published the paper The Complexity of Proving Procedures, which is where he formalized theorem procedures, that is, which is where he formalized the notions of polynomial time reduction and NP completeness, and proved the existence of an NP complete problem by showing that the Boolean satisfiability problem is NP complete. I'll talk about all that later in a moment. But it is worth noting that this paper was it created one of the most famous problems in all of computer science, that is the P versus NP problem, which remains unsolved today, and as a matter of fact is one of the 7 Millennium Prize problems, which are the 7 unsolved problems that have $1 million bounty on them. His work in this paper won him a Turing Award 11 years later in 1982. So he's been granted the highest honors a computer scientist could possibly ever ask for. To truly appreciate why Cook was important, though, we have to understand what exactly it is that he showed. So we have to understand what we're talking about. First, what is polynomial time reduction? Well, in the time of the paper that the paper was written, computational complexity was a very new concept. They were just starting to explore the idea that some computational problems are harder than others. The original sort of statement being, how do we compare the difficulty of, say, addition and multiplication, right? How can we quantify the difficulty of addition in a way that allows us to compare it to multiplication, or vice versa? So this is how polynomial time computable functions came around. Then there's polynomial time reduction, which is a method for solving one problem using another. In that way, you can compare the problems. So one shows that if a hypothetical subroutine, a subproblem, you could say, if you can find a subproblem solving the second problem exists, then the first problem can be solved by transforming it or reducing its inputs for the second problem and calling the subproblem one or more times, i.e. recursion. So you break a problem down into subproblems and then solve up, which is important for NP completeness. So what is NP completeness? Well, in short, it's a category of problems that are difficult to solve quickly, but are easy to verify once you have a solution. A bit more thoroughly, though, a problem is considered NP complete when it satisfies 4 conditions. The first is, for any input to the problem, there's a Boolean output, a yes or a no, a 0 or a 1. That is, it's what's known as a decision problem in computational complexity theory. When the answer is yes, this is the second condition. When the answer is yes, this can be determined through the existence of a short solution. But a short solution is not very mathematical, so it's defined as one that is of polynomial length, hence the discussion of polynomial time reduction. How can we get it as short as possible? The third condition is that the correctness of each solution can be verified in polynomial time, and a brute force algorithm can find a solution by trying all possible solutions. Fourth, finally, the problem can be used to simulate every other problem for which we can verify quickly that a solution is correct. That is, if you found the solution for one answer, it should be simple to find the solution to any more. Now, we didn't know, or at least we couldn't prove, that an NP-complete problem existed until Cook cooked one up. He proved that the Boolean satisfiability problem is NP-complete. Well, what's the Boolean satisfiability problem, I hear you ask? The Boolean satisfiability problem asks whether the variables of a given Boolean formula can be consistently replaced by the values either true or false in such a way that the formula evaluates to true. So If this is the case, the formula is called satisfiable. If no such assignment exists, the function expressed by the formula is false for all possible variable assignments, and the formula is called unsatisfiable. For example, the formula A and not B is satisfiable because one can find the values A equals true and B equals false, which makes A and not B true. Hooray. But in contrast, A and not A is unsatisfiable. As for either A equals true or A equals false, A not A will always be false. A isn't and not A. It just doesn't work. Now, it sounds kind of simple when you put it that reduced, but to prove NP completeness is a whole other beast, right? The NP completeness of this is far more difficult to show. And if it were easy, he would not have been given a Turing Award for it. So that brings us to the final part of his paper, which sort of introduced this P versus NP problem to the world. And the P versus NP problem is one of the 7 unsolved problems with a $1 million bounty, right? Those millennium problems. It's worth noting, though, they aren't unsolvable. They are just unsolved. And that was proven kind of in 2010 when one of the problems, the Poincaré conjecture, was proven. So if you, the listener, solve the P versus NP problem, you should send me the solution first. Since, I'm the one who told you about this, we can at least maybe split the prize money or we'll figure something out. But what is it? The P versus NP problem. Well, it asks whether or not for all problems for which an algorithm can verify a given solution quickly, that is in polynomial time, an algorithm can also find a solution, can find the solution in polynomial time. So, think about it like this. The solution to this problem is vital in so many ways and in so many fields, and most notably in computer science, cryptography, right? If P were to equal NP, if we knew P equaled NP, that would throw the field of cryptography into complete disarray, because so much of cryptography relies on the fact that some problems are extremely difficult to solve if you don't know the solution, but are easy to solve if you do. Think symmetric ciphers like AES. Those would fall apart. Mining Bitcoin, for example, would take less than a second, and it would likely have to dissolve as a currency. And the public key cryptography would be so insecure, it would make the money in my money jar I leave on my desk look like Fort Knox. So the P versus NP problem, if solved, will have extreme consequences, not only in the world of computer science, but all over the world. So shout out Stephen Cook for presenting this to the world. And that's all, folks. That is Stephen Cook and his greatest works. I hope you enjoyed listening to me talk about Steph Curry.